Electrochemical series. By taking standard electrode potential of hydrogen electrode as 0, standard electrode potentials of a large number of electrodes have been determined. When various electrodes are arranged in order to increasing or decreasing values of their standard reduction potentials, we get a series called electrochemical series. Nernst equation. Nernst equation shows the relationship between electrolyte concentration and its electrode potential. The electrode reaction is written as reduction reaction. Nernst equation for this reaction is given by E is equal to E naught minus RT upon NF multiplied by natural logo of Q, where Q is the reaction quotient. It can be represented by M upon M ion. Put the value of Q in the above equation. We get E is equal to E naught minus 2.303 RT upon NF log M upon M ion, where E is equal to electrode potential under given concentration of electrolyte, E naught is equal to standard electrode potential, and N is equal to number of electrons involved in the reaction, T is equal to temperature on Kelvin scale, F is equal to 1 Faraday, R is equal to gas constant. At 298 Kelvin, put the value of R, T and F in the above equation. We get E is equal to E naught minus 0.0591 upon N log M upon M ion. For pure solids and liquids, molar concentration is taken as unity. Now, the above equation becomes E is equal to E naught minus 0.0591 upon N log 1 upon M ion. Nernst equation and EMF of the cell. EMF of a cell constructed from electrodes in non-standard conditions is given by E cell is equal to E naught cell minus 2.303 RT upon NF multiplied by log Q. At 298 Kelvin, this equation becomes E cell is equal to E naught cell minus 0.0591 upon N multiplied by log Q. Here, E naught cell is equal to standard cell potential, N is equal to number of electrons involved in the balanced chemical equation of cell reaction, Q is equal to the reaction quotient which is derived from balanced equation for cell reaction. Let us consider that the cell reaction is AA plus BB gives rise to CC plus DD. The value of reaction quotient is given by Q is equal to C raised to the power C into D raised to the power D divided by A raised to the power A into B raised to the power B. The EMF of the cell is given by E naught cell minus 0.0591 upon N multiplied by log C raised to the power C into D raised to the power D divided by A raised to the power A into B raised to the power B. Nernst equation and equilibrium constant. An electrochemical cell works as long as there is a potential difference between anode and cathode. As the cell operates and cell reaction progresses, there is decrease in the concentration of electrolyte at cathode side due to deposition of ions on the electrode, and at the same time there is an increase in concentration of electrolyte at anode side due to dissolving of metal in the solution. Consequently, electrode potential of the cathode decreases and that of anode increases with the passage of time. Ultimately, at some ratio of concentration of the electrolyte at anode side to that of the electrolyte at cathode side, the electrode potentials acquire the same value, and therefore the cell potential becomes zero. At this stage, the electrochemical cell stops working and the cell is in a state of equilibrium. By knowing standard EMF of the cell, equilibrium constant for the cell reaction can be calculated as E naught cell is equal to 0.059 upon N log Kc. Electrochemical cell and Gibbs energy. The reversible work done by a galvanic cell is equal to decrease in its Gibbs energy. If the EMF of the cell is E and NF is the amount of charge passed and delta Rg is the Gibbs energy of the reaction given by delta Rg is equal to minus NF E cell. If the concentration of all the reacting species is unity, then E cell is equal to E naught cell. Delta Rg is equal to minus NF E naught cell. By calculating the value of E naught cell, we can obtain the value of standard Gibbs energy of the reaction delta Rg naught. Standard Gibbs energy of the reaction and equilibrium constant are related by the equation delta Rg naught is equal to minus RT natural log K.